We present a new method for resolving frictional contacts between smooth elastic objects. Our method uses implicit surfaces to produce high-quality contact patches between deformable materials. In this example, a hand grabs a whiskey glass between the index finger and the thumb. The fingertips deform, producing large contact patches adhering closely to the glass.
In contrast, traditional contact solvers use polygonal surfaces for collision detection. We drape a cloth on a stationary polygonal cylinder to show how this approach can lead to sliding artifacts. In each row, the resolution is increased from left to right. The top row demonstrates the method by Lee and colleagues from 2018, while the middle row shows the same example in Houdini's simulator. In the bottom, our method shows consistent sliding behavior that is independent of resolution.
Additionally, explicit methods for friction can severely underestimate true friction forces, since sticking is not guaranteed at the end of each time step. Here, the first three cylinders from the left, showing Houdini's simulation, fail to adhere to the sliding cloth regardless of resolution. Our method on the right is able to maintain stable sticking even at the coarsest level. By using a smooth contact surface, our method can generate smooth sliding even at the coarsest resolution, as shown on the right. On the other hand, with polygonal contact solvers, polygons may align during contact, producing additional artificial friction as demonstrated here by the middle two cylinders. On the highest resolution cylinder on the left, the cloth slides, although not without collision detection artifacts. By varying the coefficient of friction, we can achieve a variety of sliding scenarios. We can also get a consistent sliding behavior as we shift the initial position of the cloth. To demonstrate the accuracy of our friction solve, we drop an elastic block on a 10-degree slope. Our method successfully stops the block when the coefficient of friction is just above the theoretical stopping value, but it lets it slide off for a smaller value as expected. For a point of reference, we included Houdini's simulation on the top. Our method can reproduce the stick-slip instability phenomenon on the legs of a stool sliding down a subtle slope. We drop a tennis ball with a clockwise spin on a slope to produce a deflected bounce followed by a transition into rolling. With the highest coefficient of friction, the ball bounces back and forth as friction converts elastic potential into kinetic energy. We simulate a simple belt drive mechanism where an animated driver pulls an elastic belt around a larger elastic cylinder. With a sufficiently large coefficient of friction, the kinetic energy of the driver is transferred to the elastic cylinder through the belt almost immediately. Lowering the coefficient of friction between the belt and a large cylinder causes it to slip through the belt before coming to a complete stop. We drop another hollowed ball on a trampoline to show a more complex coupling that is consistent even at lower resolutions. Here's the same example at a higher resolution. Finally, we demonstrate how our method can be suitable for cloth fitting applications, where friction is critical for generating an accurate fit. A row of animated armadillos is trying on tank tops. The one on the left wears a frictionless garment, which rests too low to cover the torso. The armadillo on the right has a positive coefficient with the tank top, which rests comfortably on their shoulders. Real armadillos are elastic, and tank tops fit differently on elastic armadillos. Here we can see how friction can transfer tangential motion between the cloth and the body. Thank you.